In this part of the lecture, we are going to focus on the dynamic modeling. So we are going to talk about the interaction diagrams, namely sequence and the communication diagrams. And if we talk about the design road, we are in the design phase at this moment. So we have already talked about the use case diagrams, the operation contracts, and the system sequence diagrams. And now we are going to talk about sequence diagrams. So in UML, to show the interaction of the objects, we can use the interaction diagrams. And for interaction, there are two specialized UML diagram types, namely sequence diagrams and the communication diagrams. And one more addition in the UML 2.0 is interaction overview diagram, which we are not going to discuss in this lecture, but this only is an addition in UML 2.0. And out of the sequence and communication diagrams, we are going to focus more on the sequence diagrams as it is more notationally rich and very expressive. So here you can see one example of the sequence diagrams, and this format here is technically called the fence format of the sequence diagrams, where you can see that the time is increasing in the downward direction, whereas the method calls are from left to right. This rectangle at the top shows an instance of class A, whereas this rectangle here shows an instance of class B. More specifically, you can see that this myB is a named instance of class B, whereas if you do not write any name here, that means this is an anonymous instance of class A. And if you would like to translate that sequence diagram into code, where I explained that the sequence diagrams are going to help us generate the bodies of the methods, you can see very clearly that we have different elements involved in the sequence diagram. So the information which can be taken from the sequence diagram includes that there is a class A on the object of which we are calling a function called do1. So the possible information that we can take from this sequence diagram is that there is a class A which contains a method called do1, and from within this method body I am calling two different methods called do2 and do3. But one important thing is that whenever you call a method, you should call it on an object. So the object on which I am calling these two methods is the object of class B, and the name of the reference variable or the instance is myB. So to see that in our code, I can very clearly see that first I'm creating the object of class B so that I can call these two methods here. So I'm referring or naming it as myB, and from within the method I'm calling myB.do2, and then I'm calling the function called myB.do3. So in short, this class or code represents this sequence diagram. Another way for representing the same stuff is called the communication diagrams. So the communication diagram can be used to show the same collaboration, but it uses a network or graph format. So we have a function called do1 which is present in the unnamed instance of class A, and then from within that function call I'm calling two different methods, namely do2 and do3, and these methods are being called on the reference or instance of the B class. So there are definitely some differences between sequence and communication diagrams as they both are used to show the interaction, but the sequence diagram clearly shows the sequence or time ordering of the messages, which cannot be seen in case of communication diagrams. Additionally, the sequence diagram is a large set of detailed notation options. As we move forward, you will see there are a number of possible notations which can be used with the help of sequence diagrams. And in terms of space, it is going to consume the horizontal space, and the sequence diagram is forced to extend towards the right hand side. As we add on new objects, the new objects are going to be added towards the right hand side of the diagram, and as the time increases, it expands towards the vertical space. Whereas communicational diagrams are space economical, but they are more difficult to see the sequence of messages. You really cannot tell which message occurs when, and after which message what message should be called. And similarly, there are few notation options in case of the communication diagrams. So we can see that sequence diagrams are rich in notation. They can be used with most of the options and scenarios, and they also show our time ordering or the sequence of the messages that take place. Here as an example, we can see this sequence diagram includes three different classes, namely register, sale and payment class. And to see the sequence of messages, we can note that someone sends make payment message to register. So we are calling or sending a make payment message to the register class. And then register sends make payment message to the sale. So register is going to send the make payment message to the sale class. So that means we are going to have an object of the sale class, and on that object we are going to call that make payment method. And finally, sale creates an instance of payment. In response to this make payment method, this sale class from within this method creates the instance of payment class. What you must notice in this scenario is that it is not known that who created register or sale objects. As you know that this register and this sale object is not having any lines which represent when they are created. In contrast to that, this payment object is known to be created by this create call. These scenarios can be confusing at times while you're modeling, but in this case it is pre-assumed that register and sale objects were existing when we made a call to the make payment method. So you can have a look at this code to understand the translation of the previous diagram. So from the sale class, we have inside the sale class we have the payment reference variable, but the object of this payment will only be created when you call the make payment method. And from within the make payment method, we are calling the new keyword, calling the constructor of the payment class, passing the cache standard, and in return creating the object. And here we can see the same collaboration, but this time using the communication diagram. So we are having the make payment where this arrow represents the direction of the messages. This message is made to the register class, and from within this message we are making another message called make payment and passing the cache standard. And this cache standard is then used to create the object of the payment class by simply passing the message create. One thing that you should notice here is whenever we want to create new instance within the sequence or communication diagram, we can write the word create. So it can be part of a notation that when you are writing the word create, that means you are going to create the new object of that particular class. So guys, those small boxes that you have been seeing in the sequence diagrams are actually called the Lifeline boxes. And here in this slide we can understand the different representation of those Lifeline boxes. Whereas, just for your information, this line here is called the Lifeline. So the Lifeline box here is representing an instance of class sale, and to be specific, this instance is an unnamed instance, and this is because we are not writing any name before this colon here. Then we have a named instance of the class sale as we are writing it, so we have S1 as an instance of the class sale. This Lifeline box here is representing a meta class, so we can explicitly use this notation to mention if there is some additional information to be displayed. This Lifeline box here is representing an array list, and this array list is of type sale, whereas I'm naming this array list as sales. If you want to show a particular single element from within the array or the array list, you can simply name it with the help of the index, and this represents here that this is of type sale. And if you're using the list interface in Java, you can simply write the name of the interface, and this X represents single element from within the list. When we are creating the sequence diagrams, we might have different possibilities of writing the syntax for the message expressions. So what we can do is to write the name of the message with the parameter name, or we can write the name of the message without the parameter name. Whereas in this third example, we are calling or sending a message called get product description with the parameter ID, and this D represents that this product description returns a description which will be stored in D. Whereas in addition, we can also use a colon with the parameter to represent the type of the parameter. And here we can use colon with the function or the message to represent the return type of the message. So it is entirely up to you that which particular syntax you are going to use. So you can either choose any one of them, or you can use the combination of those. For further understanding of the sequence diagram notation, let's have a look at this example where I'm calling or passing a doX message, and this message is usually called a found message. And what happens is that the sender of this message is not specified. So here you can see that we do not know the sender of the doX, which is in contrast to the sender of do A, do B, do C, and do D. Similarly, this solid bar here represents the scope of doX. So when you called doX, the scope keeps there until and unless this solid line continues. In other words, you can say this is an execution specification. So this execution specification bar indicates the focus of control. So here we can clearly see that from within the doX method, which is there in the register class, we are calling three different methods. The first one is do A, which is called on the sale class. The second one is do B, which is called again on the sale class. And the third message is do C, which returns where from the body of do C we are calling another method, a fourth one, which is called do D, and it is being called reversely on the register class. With the help of sequence diagrams, we can also represent the singleton objects. So basically singleton objects or singleton classes are those classes which have only one instance. So you cannot have more than one object of a singleton class. So in case you have a singleton object or class, you can put this one, a small one, on the top right corner of the class to represent that the object of this store will only be 1 and 1. So that's very obvious. In our point of sale system, we will only have one object of this store class. To specify the reply or returns, we can have different possibilities. So for example, this one is a more common syntax which represents that you are calling or passing a message do X on the register class, and from within this message we are sending another message called get date, and this get date message has a return type which is being represented with this D1, and this also represents that this return value will be stored in D1. Another way of representing a return value is with the dotted or dashed line. So when you call this get date message, it shows that in response this A date is being returned as the return value. So these are two different possibilities of representing reply and returns, but this first one here is most common way to do that. Whereas in addition, you must know that representing the responses or return values are actually considered optional. One other arrangement could be where when you call a function on a class, in response to that this sends a message to itself. So objects commonly invoke their own methods. So if you want to illustrate that in response to this do X on the register class, another method of that class is being called on the self object, you can use this loop arrow here. So one more possibility is the creation of instances, which can be represented in the sequence diagrams. So for that, what we can do is to call the create message and then pass the value with which we need to create the instance. So in this case, we are going to create the instance of payment class. So as a result of the message make payment, we want the instance of the payment to be created. So the create actually creates the object or instance of payment class, and this object is an anonymous object. And then later on we are calling the authorize method or message on the same newly created instance. Now one important thing that you must keep in mind is the height at which we are placing this newly created instance, and this is placed at the height of its creation. And you can see the height of this new object or instance is as per the create message, and it is different from the height of the already existing objects. Now one other important factor is the dashed line. So you need to represent the newly create call with the dashed line in contrast to the solid line that we use for simple messages. Now if you want to destroy the messages, you can use the destroy stereotype, and you can end your lifeline with the help of an X or a big cross. So it says that the destroy stereotype messages with the large X at the short lifeline indicates explicit object destruction. So when we created the new payment object, we called a number of methods on that object, and finally we destroyed it. And this vertical coverage demonstrates the life cycle of an object. So it says the sale object is there until and unless this lifeline is there. Well, the representation of the destruction is not necessary when automatic garbage collection is there. For example, in Java, we might not need to represent the destruction of the objects as automatic garbage collection is there. There are also different types of frames in the UML, and with the help of frames we can represent different extraordinary situations. Different types of frames may include loops, opt frames, alt frames, parallel frames, or the region frames. So the region and parallel frames are used for multi-threading, whereas loops are used to represent the loops. So in this example, we are creating a loop, and in this loop we want to enter multiple items. So this loop at the top left corner represents that this frame is specifically for representing a loop. So we enter multiple items in this loop, and we keep on entering the items until and unless we have more items. And every time this message enter item returns us with the description and the total. In this example, I can clearly explain the usage of the loop frame. But in addition to that, we are also providing the condition for the loop. Plus, we are telling the increment size. So if you want to increment it by 1, I will say I++, else I can say it as I+2. And to represent the conditional messages, I can use the same frame, but in this case, I'm going to use the opt word here. So this opt represents that this frame is a conditional frame. And to mention the condition, I can use these square brackets and saying that the condition is on the color and the value for the color should be red. To represent the scenarios where we are nesting, probably we are nesting a loop in a condition, or we are nesting a loop within another loop, we can nest a frame within another frame. And just to mention for your information, One of the older styles for representing a conditional message also exists without the use of the frames, where in this case the condition is being put in the square brackets with the message name. And you can observe that I am not using any frame here. To represent the mutually exclusive conditions, or if-else conditions to be specific, we will use the alt frame. And in addition, we can specify the section or the division between if and else statement with the help of this dashed line. So if x is less than 10, we will send the calculate message to B class. Else, we will send this calculate message to the C class. So this frame shows mutually exclusive interactions. If you think that a part of your sequence diagram needs to be separated into another diagram, you can use the reference frames. So in this example, I'm using two reference frames just to refer two different sequence diagrams from within this diagram. So what I can do is I will simply write two different sequence diagrams, and whenever required, simply by mentioning the name of those diagrams, I can use the reference frame and link them up with my parent sequence diagram. This will be it for now for the interaction diagrams. For further reference, you can go and read chapter number 14 and 15 from applying UML and patterns. Good luck!